So now we get to the fun part, which is to derive the solution for the principal component analysis problem as we stated earlier. So as we covered just a minute ago, the PCA problem involves finding the set of orthonormal vectors, or in other words, an orthonormal basis, which we'll call this phi1, phi2, phi(m). Each of these should have a bar on top to indicate these are vectors. So the goal is to find this set of orthonormal vectors such that the model, the linear model, composed as the linear combination, the weighted linear combination of these basis vectors, fits the data set, some data set that we've been given, x1, x2, xm, etc., in some optimal way. And as we just covered, we can, whatever data set we're given, we can initialize the data set by removing the mean, essentially computing the mean of the data set and then replacing each data point by the same data point with the mean subtracted. Right? And so we would like to find the set of bases, m of them. Typically we're talking about dimension reduction, so we'd like m to be less than less than d, which is the size of each of these vectors. So let's compute the solution to this problem. So let's write down the sum of squared errors between the model approximation to each of the data points, right? So I'm going to write QB now. B here is the set of vectors phi1, phi2, phi3, etc. As we just talked about, we assemble all these vectors into a matrix B. So we're going to optimize this function, this Q as a function of B. And let's compute the error between this model and the average error between the model and all of the data points, right? So we sum from k equals 1 through n. And for each of these, we compute the least squares projection of the model, of the data into the space of the model. So for each of these data points, we have an internal minimization problem to solve here. As we just covered, this minimization problem has a closed form solution. It's a linear least squares problem. So here we plug in the solution C, which is simply B transpose xk, right? Taking advantage again that we are requiring this set of basis vectors to be orthonormal with respect to each other. And if we open up this norm vector here, is the vector transpose times itself, and we do all of these cross multiplications and group the terms. So first we do all the cross multiplications. Here is this times that. Here we have this times that. Here we have this times that. And here we have these two vectors, right? And of course I can take this vector here and put the transpose inside, right? So when I bring the transpose inside, I have to reverse the order of all these vectors and matrices, and I end up with this reversed order here, and the vector x transpose on the other side. So this is rewritten here, and of course we're talking about the data set that we're given as real vectors, so this is equal to that, so that we just take two of these and the vector itself. So now we note that we are requiring the set of vectors phi1, phi2, etc. to be orthonormal. In other words, B transpose B is equal to the identity matrix, so this simply drops out, and we have a simplified version of our problem here. Noticing once again that once this drops out, this term here and this term are essentially the same, but we have two of these, right? So we just have 1 minus 2 is just minus 1. So I just reverse the order, put this in front and this minus term over here. And I already went ahead and wrote it in a little bit more familiar format, right? So this term, if you look, I can take the transpose of this vector and rewrite it like that. And also we can notice that this term here, or this term here, is independent of B. So in other words, if I try to minimize this function as is, this term here being there or not being there doesn't mean anything. So I can simply remove it. Moreover, I'm minimizing the negative of something, which is essentially, it's gives us the same answer as maximizing the positive of this thing. So I'm just trying to simplify things as much as possible, and I'm also removing this 1 over n here, which doesn't affect our definition of the solution either. So the summary of the situation is that the least squares problem defined by PCA is equivalent to this maximization problem. So let's look at this term here and let's see where it is. So here I'm bringing back the 1 over n up front here. Again, it doesn't matter keeping it there or not keeping it there, does it's the same. So just writing these vectors here, this is what we have. I'm expanding this out just so things are a little bit more clear, right? This is b times the x, right? Which means it's the individual basis vectors transpose times my vector, right? So it's essentially a sum of squared values, right? And this is what I'm trying to write over here. And I can also rearrange this and here, right? So phi I transpose times xk is the same as xk transpose times phi I. Again, we're talking about these being real vectors, so there's no problem with doing that. And then we notice that the sum here, which I'm summing from 1 over m, right? I have m of these vectors. I can also reverse the order of the sum, so I can bring the sum over k in front of the sum over j, over I. And then I notice that if the sum over I'll bring also the sum over k inside here, right? So we have this element here. We have two sums to deal with, sum over I and sum over k. And I'm bringing the sum over k inside only to the elements that it affects, and I'm leaving the other parts outside. And if you notice this, look at the sum now, keeping in mind that we have already taken out the mean of the data set, right? So these are mean 0. So this is essentially our sample covariance matrix, S, that we discussed before. So I just simply substitute, whenever I see this whole sum here, I substitute S for it. So this is our term. So we saw that this term here simplifies to this here. Therefore, PCA, which we already made the argument that maximize is equivalent to maximizing this guy here as a function of phi1, phi2, etc. So it's equivalent to maximizing this particular sum here, with that important constraint that B transpose B equals to the identity matrix. Again, we would like the vectors to be all orthonormal. So now let's split, keeping in mind that we have rewritten our optimization problem to look like this now. Let's take a look at this problem, and let's first take a look at a simple version of this problem. Let's consider the case where sample covariance matrix is essentially diagonal, meaning it has some values, which I'm calling lambda here, along the diagonal, and has zeros everywhere else except the diagonals, right? And let's make the simple assumption that these are already, the values here are in decreasing order. So then, if I plug S in this specific form into our problem here, it reduces to this particular sum over j now, right? Where j here is from 1 to n because S is the size of n by n, right? So this phi I here, phi ij, now we're talking about the jth element of the ith vector, right? And of course, this is squared because I'm multiplying this vector to here, but really multiplying each of the elements by a number. So it's like, and I have this in both sides, so it's like summing up all the squares of all the elements of the I vector, but of course, multiplying by the particular lambda of that dimension. And once taking advantage of, once again, that we're assuming that each of these phi's are orthonormal, which means the dot product between them gives us always 1, right? So we can understand that we can view the sum here, 1 over n, as a weighted average of our diagonal values, right? These sum to 1, so it's like we're summing all these coefficients and taking an average for them, but the average have different weights, right? And the weights are given by this guy. So, which means that if I'm summing, and they're all positive, right? They're all positive weights. So the largest is, and keeping in mind that I'm trying to optimize with respect to phi's, right? So the largest that this can be for the case of m equals 1, the largest value that this can take is when is lambda 1, right? Because keeping other elements in the mix will only decrease, right? And once again, we have already ordered the lambdas here along the diagonals already ordered in decreasing size, right? So lambda 1 is the largest value. So the largest possible value for this particular sum here should be lambda 1 if I'm taking only one m, right? If m is 1. So which means that this will happen when my phi1 equal to the canonical vector e1, which is essentially 1 and zeros in all the other entries. Right? So again, we're looking at a very simple version of the problem first, where our sample covariance matrix is given by a diagonal matrix, and we have assumed that the diagonal matrix is arranged such that the first value is larger than the second value, etc. Right? Then we see that this problem summarizes to this. And when we're looking at m equals 1, just one sample, the largest possible value for this optimization problem, which we're trying to maximize once again, would be lambda 1. Now let's look at the case for m is larger than 1. So when now we split this into this particular sum. And then, we'll show this in a little bit, but taking advantage that the matrix B is orthonormal, so which means that both the columns and the rows are orthonormal, we'll see that later. If I sum along I here, now from 1 to m, but I don't sum all n of them, I sum only m of them, this is going to be less than 1, right? If I sum all the way to n, this is going to be 1 once again. So we're going to use this, and I'm going to show why this is true later. So if I look back at my function here, I'm going to see that this is always going to be, when I include these terms here, this is always going to be less than these guys, right? So because I'm summing because this number is always going to be less than or equal to 1. So that's kind of trivial. So therefore, by the similar argument as before, the maximum value that the quantity we're trying to maximize can obtain is this, right? And this maximum value will be obtained when my phi I equals to ei by a similar argument as before, right? So to summarize what we have done so far, we looked at the Pca problem for when the sample covariance matrix is a diagonal, which means in this application, which means that the samples across dimensions the covariance is 0 or the correlation is 0. Then minimizing the sum of squared errors between the model and the data under the assumption that B is orthonormal. The solution will be given by B equals to the identity, which means our eigenvectors, our PCA components are the let's say the canonical vectors E1, E2, E3, right, where EI essentially here, where EI is 1 only at the ith entry of the vector, right? So that's our EI. So that's a simple version of the problem, but of course we can't always assume that the sample covariance matrix will be as simple as that. But taking advantage, so let's look at the general case. We're going to take advantage that the sample covariance matrix in this case is real and symmetric and positive semi-definite, right? So we're not going to show this in this video, but under those circumstances, we have an eigendecomposition that is kind of simple. So S is given by V lambda matrix V transpose here, where this matrix here are what we call the eigenvalues of S, and the V here is a matrix where the columns are the eigenvectors of S, right? So this is your standard eigenvector decomposition for real symmetric matrices. So plugging in this decomposition, which always exists for this type of matrices, into our definition here, we see here's our decomposition. Then we can momentarily, I'm going to define this Qi vector to be V transpose Phi, right? And every time we see phi here, there should be a bar to indicate this as a vector. Then this quantity here can be written in terms of these Q components, which essentially is the problem we just saw before, right? So if we look at this problem this way, the solution is already given. There Ki equals Ei, right? Our canonical vectors from before. So that's given. Where now Ki is V transpose Phi, right? Which means it's which is given by Ei, as we just made the argument for. So of course, this matrix here, this matrix of eigenvectors is orthonormal. So V transpose V is the identity, and so is V transposed. So if I multiply this here both sides by V, I get my Phi back. Right, so this is Phi. The scanning didn't go through completely here. So in conclusion, right? So what we're concluding here is that we started with a least squares problem that said QB equals this, and we would like to minimize this Q over B, right? And B is again our matrix where each column is composed of a basis vectors, and we're assuming that these bases are orthonormal, so B transpose B is the identity. We also assumed we have pre-processed the data to remove the mean. Then minimizing this is equivalent to maximizing that, right? Where S here is now our sample covariance matrix for zero mean data. And we would like to find the set of Phi's, or B, that maximize this thing. The solution is given by B equals V. Essentially, the eigenvectors of S are the Phi's. And this procedure is known as principal component analysis. And that's the summary of it. So we already saw the summary for this procedure. First, you center the data, means subtract the mean. For the entire data set, you compute the sample covariance matrix of the zero mean data. You take the eigenvectors of this sample covariance matrix, and those are your principal components. So the only thing that we're missing here is to explain why this particular sum that we used earlier is less than or equal to 1. Right? So let's consider this matrix C, which now is n by n, because let's consider the version of the matrix where I take all possible vectors, right? So if I have vectors of n dimensions, as many points as I have the size of the matrix, size of the vector, and the number of vectors that I take are the same, and I'm going to call this n momentarily. Then C transpose, and again, once again, these are orthonormal, so C transpose C equals to I. which means the inverse is the C transpose, so I can take C times C transpose, that's again I. But that's not our identity, right? So we're summing, so if the matrix was square, summing along the rows and summing along the columns would give us that these sums are all 1. But if I'm not summing all n of them, but I'm summing m of them, then this inequality should hold. Why is that? Let's look at, let's expand this matrix now, where we have m, and m is less than n, so we have the size of the vector is still n, but we only take m of them, and to multiply b times b transposed. And so let's look at a particular row here, right? A row multiplied by this column. Because if I sum over I, if I sum all n of them over I would have 1. And because each of these are that I'm summing here, right? So this is this times that is this times that. So I'm summing all squares, and because these are all positive, if I don't sum all of these, all n of this, I've summed only m of them, then it has to be naturally less than 1, right? So this is the identity we were missing, which this is what we used up here to show that here we use this identity over here, and this is what we owed you to show this, so you can understand the solution of PCA, right? So once again, the PCA solution is very simple. All you have to do is compute your covariance matrix of the data, and the eigenvectors of this matrix S here are essentially your principal components.